This is the attention to detail that ensures every Trent engine is as safe and efficient as it can be. And with up to 150 blades leaving the factory every week, it's also the challenge that keeps Mike going.
For me, it's exciting. After 27 years working on fan blade, it's still exciting. There's still a lot more to do.
Rolls-Royce is a global company. Some parts of the engine are made and assembled at factories abroad. Getting them to the UK is Kath Taylor's job.
This is the turbines purchasing department, where we source parts from all over the world, and my role in particular is to source the modules from mainland Europe. We're talking probably at the moment about 10 modules a week. Very occasionally we're affected by the weather or the ferries, but the bulk of the modules do arrive on time.
It may be a global company, but the biggest single module is manufactured at another of Rolls-Royce's specialist factories just 50 miles down the M1. Mark Reed is in charge of building the massive protective case that shields every engine's fan blades.
The fan case's primary function is to guide the air through to the main core of the engine and to provide a containment system in the event of a blade off. When the forging's originally constructed, it weighs 5 metric tons in weight, and then when it's finally finished machined, it weighs roughly 500 kilos. So we have to take a large amount of material off, and we have to machine it down to some very fine tolerances. Typical wall thicknesses can be around 2.5 millimetres. There's a number of different processes that take place, typically around 40. A component can spend up to 90 hours in the machine. So we put it on at the beginning of the week and we take it off at the end.
And nothing goes to waste. Every sliver of precious material is collected and recycled to make more components. Mark runs a team of 140 top engineers, including experts in the most essential skills, turning and welding metal. One of the most experienced is welder Bob Blackwell. His job is to fix in place a ring of titanium blades that'll channel air smoothly into the engine. It's a highly specialised form of welding.
I'm a TIG welder, come sheet metal worker. I've been doing this job for 22 years now. All these vanes are different cambers to achieve the best airflow. Every weld on this job will be x-rayed in the x-ray, so any defects have to be taken out, obviously repaired then and put right. When this weld's finished, this vane should leave a tolerance of no more 5 mil radially and 1 mil forward and rearward on the blade. It's not machine, it's hand skill, and we think that's a fine tolerance to achieve on a hand weld.
Bob works at the factory alongside his son, Lee.
Lee's a sheet metal worker, they're just the same as myself, so when Rolls were recruiting, I asked me if he fancied joining the company.
I see my dad made a good living out of it, so I decided to get a trade and just get the same trade, really.
Lee's a better welder than I am, better craftsman than I am. They don't need that. They don't need my voice. He's quite capable on his own, really.
For this family partnership, the factory life certainly seems to promise a good future.
Yeah, I hope so, yeah. Wouldn't like it to come to an end too soon,
At the heart of every engine is a ring of 96 turbine blades that are the most amazing components in the whole engine. Jet engines work by sucking air into the core and through multiple compressors. Squashed to a 50th of its volume, this air is forced into a combustion chamber, where it explodes with fuel to create a ferocious gas jet. This jet is met head-on by the turbine blades, spinning them so fast that each blade delivers the same horsepower as a Formula One engine. The job these tiny blades have to do is unbelievably demanding.
The blade exists in a fairly harsh environment. It has to rotate at about 10,000 revolutions per minute, the blade speed of about 800 miles per hour. The component itself operates at something like 300 degrees above the melting point of the alloy.
To operate at around 1700 degrees, they're designed not to melt.
Here you see the gas streams moving around the airfoil. At the bottom of the blade is the fir tree area, which is used to hold the blade into the disc. Above it you see the aerofoils with a peppering of cooling holes.
To stop the blade melting, Rolls-Royce designers used computer modelling to design a blade that has a precise pattern of tiny air passages throughout.
Here we see what the blade would look like if we didn't have it cooled. And you can see that there are some areas of red, which means that the component is too hot. We put a cooling system inside of the blade, which cools it down to safe levels, and that cooling system takes away the same amount of energy that would boil a kettle in a 20th of a second.
But even with the cooling holes, no ordinary metal would be good enough. That's where the company's Materials Research Laboratory comes in, creating new metals with exactly the physical and chemical qualities demanded by the designers.
To try and achieve the properties that the designers want, we will design some trial compositions of alloys with different recipes, different blends of the alloy and constituents, and then we will test those samples and different mechanical and environmental tests, and from that we'll choose the best possible blends which will deliver exactly the balance of properties that they require.
Using electron microscopes, the materials scientists can precisely analyse the microstructure of the alloy, checking that the crystal structure and mixture of metals is exactly as intended.
We've got a team of research specialists, about 25 in the team here in the UK, and there are teams in Germany and the States as well. And we're trying to draw on all the expertise that exists in the academic network around the world to bring all the best expertise we can into Rolls-Royce.
Even the finely balanced alloy recipe isn't the most advanced technology in the turbine blade. To cast the metal into its complex shape, a unique process is used, and it's another very closely guarded secret. It's done at a purpose-built foundry in Derby, where one of the few people who knows the secret is casting engineer Owen Draper.
If you take a normal piece of metal and solidify it from being molten, you'd end up with something that looks a bit like a granite worktop. Lots and lots of little different crystals, all in different directions. That's not very strong because the different crystals, the joins and the boundaries between them, they just cause a weakness. So what we aim to do here is to create a single crystal. Single crystal, no crystal boundaries, therefore it's an awful lot stronger.
The blade is made by growing a single crystal of metal into the correct shape. It's incredibly complex and demands a huge team of people working round the clock. But it starts with an intricate, hand-built model of the blade in skilled hands like Maureen Hankey's.
I've been doing it on and off since '73. Skill is you've got to be very dexterous, everything's got to be perfect, everything's got to be smooth.
The secret part is the way the molten metal is cooled through a spiral tube at the base of the mould. The tube prevents all but one crystal of solid metal from passing through, allowing that single crystal to grow throughout the mould. Imperfections could ruin the casting at any stage. Even the wax models are X-rayed by keen-eyed inspectors like Jackie Brown.
We're looking for defects in the core, i.e. cracks, chips, voids. When it's sentenced to scrap, is broken in half and put into the bin.
once cast, every single blade is thoroughly checked, and checked again. By eye, by computer, and by X-ray. Even then, they're far from ready. Each blade goes through another 4 days of precision finishing in the hands of machinists like Steve Ball.
We're all very good at what we make. We don't sometimes share it. It's not until you see Trent Fleet fly over, I've made my own good bit of that.
And because of the extraordinary demands on the blade, its dimensions must be accurate to within 1/10 of a hair's width.
We grind the fir tree to within 7 microns, which is a hell of a tight limit. Goes under a load of 18 tons, that does. If we stretched it with 18 tons, re-gauged it, there would be nothing. Everything would be to the micron the same. There's no alterations in the structure. There's no cracking. There's no stretching of anything on there. And bearing in mind, you've got 96 of those in an engine set. Every one is like the first one. It's perfect. It's like a brand new baby. You treat it like that. That's why the focus of everybody in the shop's the same, whether it's 6 in the morning, 6 at night, 12 at night. Everybody's the same. The next one's always the most important, because all the rest are good. Because we've never had one come back. You can't argue with that.
It's the skills of people like Steve and the cutting-edge technology that keeps Trent engines ahead of the game. But innovation is a risky business. Designing the Trent engine almost brought Rolls-Royce to its knees. In the early 70s, the company risked everything on a revolutionary new engine for one of the world's first jumbo jets, the Lockheed TriStar.
The production programs at Derby, by modern-day standards, were very low in volume, and Derby was, a relatively small player in the aero engine market, although the only player outside of the United States in the commercial market. So getting the TriStar program was absolutely vital.
As a small player, Rolls-Royce had big ambitions.
Well, the 211 was quite an advanced engine concept, even by the standards of the day. It was the first 3-shaft engine, whereas the competitors were offering 2-shaft engines. So as well as the technological advances, it was a completely new architecture.
The design made the engine lighter and more efficient. It promised a crucial reduction in running costs and cheaper airfares. But actually building the engine proved harder than anyone expected, and the costs spiraled with every advance they made.
And all of these were put together in an engine number 10,011, which ran on February the 3rd, 1971, late in the afternoon. And the results were quite exceptional in that they were very much better than anything we'd run before. So understandably, we were quite elated.
It seemed the company was about to achieve its goal with their new engine, but the elation was short-lived.
Until the next day, when in the middle of the morning we were all invited to go into the office and the announcement was made that the company had gone into receivership.